All right, let's find the volume between these two paraboloids. Z equals x squared plus y squared, and z equals 4 minus x squared minus y squared. So just first let's draw a picture, or let's attempt to draw a picture anyway. So you take, let's just draw some axes first. Whoops, x, y, z. So first of all, the paraboloid z equals x squared plus y squared. So even in the case when just y is 0, then z equals x squared ought to look like a standard parabola. So sorry for the perspective, but sort of that way, right? And if you just took that parabola that was here and spun it around, that would create the shape that we need roughly. Yeah. Okay. But then you've got this start up at 4, and then you actually have negative quantity x squared plus y squared. So starting at 4, and if you draw downward, there's really the same shape parabola. It's just kind of pointed the other direction. And then what happens is that these two paraboloids are going to meet up and intersect in this circle right there, right? So the intersection is a circle. Okay, so the region, if I can dare try to shade it, that's in here, right? So the region is between two paraboloids. Okay. So how about which order to integrate? That is, do we want to do a dx dy dz, or a dy dx dz, or a dz dx dy, or whatever, right? So let's figure out what the inner integral ought to be. Yeah? So to figure that out, I think we should ask ourselves which question is easiest. So we're about to ask ourselves 3 questions, and I think we're not going to try to answer any one of these questions right away. We're just going to look at the 3 questions and go, which is the easiest to answer. So if we were given an x and a y, what is, so for a fixed x and a fixed y, what is the smallest and the largest z? Okay, that's one question. It's really actually got 2 questions in it, smallest and largest. Okay, or how about this? Given an x and a z, what is the smallest? So fixed, given an x and a z, so x and z are numbers that are fixed for the moment, then what's the smallest and the largest y? Or given a y and a z, what is the smallest and the largest x? The question becomes, of these 3 questions, which is the easiest? Now, based on what we have up here, for a fixed x and y, it looks much, much easier to say what the largest and smallest z is. So I think this is, for the problem that we have right now, for the shape that we were given, the first question is the easiest, and then these next 2 questions are the hard questions. Okay, these are hard. So this, being the easiest question, tells us that the innermost integral should be the z integral. So we should integrate with respect to z first. In other words, so we'll make, this is us trying to decide what's going to be most convenient. We'll make a dz, then a d something, and a d something integral. So just to make the remark, if just parenthetical remark. If g sub 1 of x comma z less than or equal to y less than or equal to g sub 2 of a function that mentions x's or z's, if this were easier, it's not in this case, but if it were easier, then we'd make an integral that start dy, then d something, then d something. Right? So, but what we have is what's going to be easier is a dz, then d something, d something. All right. So to talk about then what's the volume? So the volume, we were asked to compute the volume. So the volume should be integral something to something, we're not sure what yet, of integral something to something, we're not sure what yet, and then the lower z value and the upper z value. The lower z value is x squared plus y squared, and the upper z value is 4 minus x squared minus y squared. Since we're trying to compute a volume, we would just integrate 1, then dz, and then d something, and d something. Now, you might say, well, if we're just computing a volume, we could, instead of had just one fewer integral and put the subtraction of the two z coordinates there, if you're kind of thinking about ways to cut on some things, sure. But for now, let's just, what if we were asked to integrate some other function, right, over a three-dimensional region? So let's just keep this with a 1 here. Now the thing to do is to project. We got this shaded in region up here, E. Now the thing to do is to project E onto the xy plane. So what does that look like? Let's copy this. Let's just copy maybe not the paraboloids themselves because they're sort of getting in the way. So what we have, I'm going to just try to draw the shape E itself. X, Y, Z. So there was this paraboloid this way, and then it intersected in a circle with the other paraboloid that, kind of lived above it like this. So it, I don't know, it sort of looks like two bowls glued together a little bit, or like a, not quite a football, because there is sort of this outer seam that's going to be kind of more pronounced and wider. I guess it's sort of like a pistachio on its side or something like that, or, where the opening is the equator. And then if we project onto the xy plane, so then, we're going to get really the shape of a filled in circle down here, right? A filled in circle is what we'll get once this is the shadow. Okay, this is what happens when we stand from up here and look down. All the points smoosh down and create this filled in circle down here. Now, if we were to draw this in the xy plane alone, we'd have, just to really clarify, that, yeah? So a filled in circle is actually called a disk. Now, what is the size of this disk? Size of that disk? Well, it's actually, remember that we had here, this was z equals x squared plus y squared, and then this upper one was z is equal to 4 minus x squared minus y squared. So we're looking for all of the points which satisfy that this z value is smaller than that z value. So we needed x squared plus y squared to be less than or equal to 4 minus x squared minus y squared. Now, if we add x squared and add y squared to both sides, 2x squared plus 2y squared less than or equal to 4, divide both sides by 2, x squared plus y squared less than or equal to 2. So we're seeing here, what we have is, the radius of this here is a root 2, isn't it? Actually, now, going back to this, we can actually reset up the integral. Okay, so the thing is, think about how the upper and lower values, this is the filled in circle, right? It's shaded inside, that's why there's an inequality. But this upper part here, you can just solve for y, right? And get that this ought to be, that the upper part ought to be y equals root 2 minus x squared, and then the lower part here, just by solving, the equation form should be y is equal to negative root 2 minus x squared. And so we can write an integral. Integral will just leave some space. We had seen earlier that the z bounds were already x squared plus y squared, and then 4 minus x squared minus y squared. We're going to just integrate the function 1, though we could have just stuck in a different function if we were given that. dz we had. Now, because we've solved for the upper and lower y values in terms of x, let's do this, dy then dx on the outside. Okay, so we'll see here that the y value goes from negative 2 minus x squared to positive root 2 minus x squared. And the x values, so when you project, you just get this right here. So from negative root 2 to positive root 2. Okay, just to make sure that we're clear with what's going on and where these numbers came from, let's just make sure, right, that what happened was we had this filled in disk here, yeah. We had at the outer edge here, this was a root 2 and this was negative root 2. And the thing was that for a specific fixed x, okay, so for a fixed x, like let's just pick like right there, x, the upper y value right here was given by, here you had at the upper y value, y is equal to root 2 minus x squared. This comes from x squared plus y squared is equal to 2. Just solve for y. And then the lower values down here, so for that same fixed x value down here, you get the y value negative root 2 minus x squared. Again, you get this from the same equation right there. Then when you project, yeah, when you're done with setting up the y bounds and you project, you'd have to project down to this, right? So when you project, let's just redraw this, project to the x-axis. Now, maybe you already see it from the picture, but the point is, if we now just draw an x-axis, then negative root 2, positive root 2. This is how the picture of the filled-in circle smooshes if all the points have to live on the x-axis. Okay, interactive question. It'd be really nice to do the following, please, is to take this integral, so given what we had at the top of the page here, integral negative root 2 to positive root 2, integral negative root 2 minus x squared to positive root 2 minus x squared, integral x squared plus y squared to 4 minus x squared minus y squared of the function 1, and it could have been a different function, but we were asked to find the volume of the three-dimensional region, so that's why there's just a 1 here. dz, dy, dx. So given this, do the inner integral. Inner integral. So, excuse me. Given this, do the inner integral, right? The one with respect to z. Then, instead of computing the integral as written, switch to polar coordinates. And then finish integrating and finish evaluating. Okay. We'll just comment that doing this is going to be a preview of what we'll look at very, very soon. This will be a preview of cylindrical coordinates. So there's your interactive question.